check. Please take your seats. These papers will still be here. They are in some kind of rough alpha order. Hopefully it's easier to find this time than they have in the past. Well, rough alpha order. I don't think they've gone far. If you have not turned in your homework paper, do so at the end of class. Don't come up to the front. If you haven't picked up your homework paper from last week, please do so after class. Okay, let's talk about PA3. PA3 was due last night, right? Tuesday, February 14 was the last extension. 12-hour grace period means I should have closed it at 10 a.m. this morning. I did not close it. So I'll unofficially extend the grace period till I get home tonight. So that you have the rest of the day to work on it. Office hours to help get through some bugs. Of course, I can't help everybody at office hours. Or whatever other lab sessions we have. What do we have on Wednesday? Just 8 to 10 a.m. and 4 to 6 after class. So there's some stuff going on after class that coincides with my office hours. So please don't everybody come to my office hours, but do get some help if you haven't quite finished it. I don't want to go past today. PA4 is now open. Not open, but it's posted. And we're going to be talking about it today a little bit, probably more on Friday. And you have a good, healthy length of time to do PA4. Okay. Anything else? Anything else on the horizon? For instance, when's the next midterm? That's going to be Friday, March 3rd. That's 2 weeks from now. Okay, let's not worry about that yet. Okay, where did we leave off last time? We're in the handout on graph theory. We talked about isomorphisms of graphs. Degree of a vertex, the degree sequence of a graph, and how most of the things that we study in graph theory, in fact just about everything, is what we'd call an isomorphism invariant. In other words, the property is preserved by isomorphism. So if you have two isomorphic graphs, either they both have the property or they both don't have the property, like connectedness, like containing a cycle, acyclicity, things like that. Those are graph theoretic properties and things that are preserved by isomorphism, and that is what graph theory is. We talked about the handshake lemma. Handshake lemma says if you add up the degree sequence, add up all the degrees of all the vertices in the graph, you must get twice the number of edges. And the proof is very simple. Every edge has to contribute 2 to the sum on the left. Right? It contributes 1 to the degree of one of its ends and 1 to the degree of its other end. And so therefore it contributes 2 to the degree, to the sum of the degrees. This is even true if we allow self-loops and parallel edges, like the other graph theorists on the other side of the earth. Right? The ones that think self-loops are included in the definition of graph and think that parallel edges, because a self-loop actually contributes 2 to the degree of 1 in the same vertex. Its 2 ends are 1 in the same vertex, but the degree of that vertex, I was very careful in defining degree. It's not the number of adjacent edges, it's the number of edge incidences there are with that vertex. That's the degree of a vertex. Was there a question here before I go on? No, okay. Okay, so I believe you had an exercise that was due today. Show that the number of vertices of odd degree must be even in any graph. How many people think they got that? Not very many, but I hope everybody at least tried. Okay. Is that the case? Well, nobody's saying anything. Yes, go ahead. Sure, go ahead.
If the sum of the degrees of all the vertices is even and the graph is odd, then there must be an even number of vertices.
It's not quite right. In order to make statements like that, you have to separate that sum into the even vertices and the odd vertices. Even vertices are those that have an even degree. Odd vertices are those that have an odd degree. The sum of any number of even numbers must be even. But the sum of some odd numbers depends on how many terms. If you have an even number of terms, a sum of an even number of odd numbers is even. The sum of an odd number of odd numbers is odd. So this trick is to take the sum in the left-hand side and to split it into two pieces. The odd degrees plus the even degrees. Now assume to get a contradiction that there are an odd number of odd vertices. Right? That's the negation of what you're trying to prove. Well, then one of those terms is odd and one of those terms is even. An even number plus an odd number is an odd number, but the right-hand side is even. That would be a contradiction. So therefore, there can only be an even number of odd vertices. Does that make sense? Okay. Well, that's in a nutshell. That was the correct proof. How many people think they got that or close to that? Okay, good. Okay, well, it's classic arguments from combinatorics. Now, a few things I didn't define when we went over graph theory in the induction handout was a few definitions, like a walk. An XY walk in G is a sequence of vertices x equals V0, V1, V2, Vk equals y. That's an XY walk in which consecutive pairs are adjacent. I.e., Vi plus 1 are adjacent, so therefore they are in the edge set of G for all I going from 0 up to k minus 1. Okay. Isn't that a path? No, that's not a path, because path excludes certain walks. But this is the most general kind of tour you can take in a graph. Start somewhere and start walking along edges until you get someplace else. There's no restriction on whether you traverse an edge more than once or whether you traverse or whether you visit a vertex more than once. If x equals y, we call the walk closed. closed walk. So if you find a walk and a closed walk, we call x the origin and y the terminus, where you started and where you end up. But of course, there's no directionality to these streets, right? These are two-way streets. You can travel either direction on any edge. So we don't really distinguish between an xy walk and a yx walk. We don't really care which one of them is labeled the origin and which is labeled the terminus. Now that will matter when we go to directed graphs, when we talk about walks and trails and paths in a directed graph. Okay, if no, let's see, if no edge is traversed more than once, we call it a trail. It is possible that a vertex is visited more than once without traversing an edge more than once. If no vertex is visited more than once, we call it a path. And I think, as I defined before, a closed path is called a cycle. Okay, we already defined that before. So this is all in keeping with our prior definition. Please take your seat, okay? This is all in keeping with our prior definition of path and cycle. Okay. Oops, that's page 2. Sorry about that. What else? Oh yeah, the length. The length of a walk, a trail, or a path is the number of edge traversals. So you could go, for instance, if this is your graph, you can go x, y, x, y, x, y, right? So boom, 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 like that. So it's the number of times an edge was traversed, and it can be the same edge. So this would be a 1, 2. So count the commas. That's how you figure out what the length is. 1, 2, 3, 4, 5. So there's a walk of length 5. It's not a trail because we are traversing the same edge many times. Okay. So that's the length of a walk. Let's define the notion of the distance. So the distance from a vertex x to a vertex y is, I may have written this down last time, it's the minimum of length of p such that p is an xy path if there is such a path, and is infinity otherwise. That's the distance from x to y. Notice the distance from x to y is a different distance from y to x, because an xy path is the same as a yx path. By the way, I have a name for this. If there exists an xy path, or trail or walk, we say y is reachable from x. So I'll use that phrase now and again. So notice that in a graph, x is reachable from y if and only if y is reachable from x. So the reachability relation is a symmetric relation. So the length of a minimum length path if y is reachable from x, that's another way to say that. Infinity if y is not reachable from x. That's the distance. So now I can state the subject of PA4. This is the single source shortest paths problem. And we'll abbreviate that SSSP. So this is a computational problem, and we wish to find an algorithmic solution to it. Given a graph G and a distinguished vertex So we pick out some particular vertex. That's part of the input to the problem. S, called the source, the source vertex. Determine delta Sx for all x in vertex set of G. So, fix a source, find the distance from that vertex to every other vertex in the graph, including itself. Notice I say for all x in V, including S. What's the distance from S to S, by the way? Can someone tell me? 0. What path goes from S to S? Yeah, it's called the trivial path. It's just like 0 in arithmetic, right? Or the empty set in set theory. The trivial path is the path where you start at a point and you stay there. We don't consider that a cycle, even though the origin and terminus are one and the same. We still don't consider that a cycle. It is a walk, trivial walk, I guess it's a closed walk, but we don't consider it a cycle. Okay. If we did, then there would be no such thing as acyclicity, because every lone vertex by itself would be a cycle. Okay, so find the distance from S to every other vertex in the graph. We can say straight away that delta SS is 0. So, given a graph, furthermore, for any x with distance from S to x finite, meaning x is reachable from S, determine a shortest SX path in G. Okay, so that's what you're going to solve. That's the problem that you're going to solve in PA4. The algorithm that solves this problem is called breadth-first search. Actually, there are many algorithms that would solve this problem. At first, you might think that's too hard. You know, that's one of those problems that can't be solved or it's too complicated, because there are many, in general, for a giant graph, there are a huge number of paths from S to X. If X is reachable from S, you know, the multiplicity of ways of getting there could be enormous, could be astronomical for a very large graph with a lot of edges and a lot of vertices. So, you know, doing a brute force search through all possible paths might be unfeasible. However, there is a very efficient way to do this. It's called breadth-first search. And you're going to implement that in PA4. Before we can really start talking about how to go ahead with PA4, though, I have to get to the end of this handout where I talk about graph representations. How do you represent a graph? After all, it's one thing for me to draw you a picture, or for me to write down a couple of sets. But how do you use that as input to a program that you're writing? So we have to talk about ways to represent graphs using standard data structures found in most computer languages. And that's done at the end of this handout. We'll get there, but probably not till Friday. Okay. Notice the use of the word A here. There may be many shortest paths. So in a way, this problem doesn't have a unique solution. I mean, there is one distance, you know, of all the shortest paths, they are all necessarily of the same length, because they're the minimum possible length. But there may be many SX paths that realize that minimum length. The statement of this problem really only requires that you find one of them. However, the requirements in PA4 are written in such a way that if you follow directions and somebody else follows directions, the shortest paths you get will be one and the same. So therefore, the output files, that's done in such a way that everybody's output files should be identical, and identical to mine. The ones that are, actually, I believe I posted, I hope I posted PA. No, I didn't post PA4. Huh? No, there are some examples. I have examples for PA4 that I haven't posted yet. All right, somebody remind me to do that if you don't see that, like as soon as I get back to my office. I'll make sure I get that posted. But I have a lot of examples of, you know, input-output file pairs, matched pairs of input-output files. And there's only one output file you should get if you follow directions. Even though there are, in general, many shortest paths. Okay. Okay, I'm not going to go over the definition of subgraph, the definition of connectedness, the definition of acyclicity, definition of tree, because we did that already. So I'm going to go to lemma 1. Lemma 1 in the handout says this: if T is a tree with n vertices, and m edges, then m equals n minus 1. Does that look familiar? It better. That was a problem on the, that's exactly where, the last example from the induction handout. I did this already. We proved this by induction. We proved it by induction on n. I'm going to prove it again by induction on m. And it's essentially the identical proof, but the induction parameter is switched to something that's one less, actually. So, where do we start? If m equals 0, you see, last time I started with n equals 1, because there's no such thing as a graph. I don't know if you remember from our original definition of graph, the vertex set isn't allowed to be empty. So the smallest graph you could have would have one vertex. However, the edge set is allowed to be empty. If m is empty, if m is 0, then t, since it's a tree and therefore connected, remember what tree means, connected and acyclic, then t being connected has only one vertex. Right? If it had two vertices, there'd be no way to get from one to the other, and it wouldn't be connected. So that establishes the base case. Another way of saying this is the number of vertices is one more than the number of edges. Okay, so 2. Remember the script now. We're supposed to show for all m greater than 0, if p of 0 and up to p of m minus 1 are all true, then p of m is true. This is the strong induction hypothesis. Assume all dominoes, starting at 0 and going up to, but not including the mth domino, have fallen. That's your induction hypothesis. Show as a consequence that the mth domino falls. And what is p of m here? P of m is this statement. I'm not going to put a box around it this time. And there should be a for all m greater than or equal to 0 out in front of the whole thing. Okay, well, I'm writing things now the way you'd normally see them in a math textbook. Okay. So, let m be greater than 0. A lot of people lost a few points on the midterm because they didn't write that sentence. Okay. Now, some people lost other points because they didn't write the following sentence. They didn't write the induction hypothesis explicitly. Assume well, assume all dominoes up to but not including the mth domino have fallen. Let's try to say that without introducing another variable. Assume for any tree T prime with number of edges in T prime strictly less than m. Okay, so that's how I say for all dominoes up to but not including the mth domino. That the conclusion is true. That is to say, number of edges in T prime equals number of vertices in T prime minus 1. That's the explicit statement of the induction hypothesis. So, in other words, the theorem is true for anything smaller than m edges. Okay. Now let's do, so what must I show? We must show if T has m vertices, n edges. Notice I very carefully used a different letter here than I'm using now. It's critical that you do that. I must show if T has m edges and n vertices, then m equals n minus 1. Okay, that's what we need to prove. Okay. How do we proceed? We're going to do exactly what we did last time. The proof isn't any different. I'm just repeating it for you. This is review. Well, I guess it's worthwhile because something like this, I mean, look, one of these things I'm doing today is going to, I guarantee, will be on the midterm, maybe more than one, the next midterm. All right, so what did we do last time? We picked an edge and we just erased it. Pick any edge E in edge set of T and remove it. This results in two subtrees. Call them T1 and T2, each with fewer than m edges. In other words, number of edges in Ti is less than m for I equals 1, 2. Right? It's my way of saying both those inequalities in one. By the induction hypothesis, we have that the conclusion we want is true for these two trees. So number of edges in T1, well, let's just try to say them both at once. Number of edges in Ti equals number of vertices in Ti minus 1 for I equals 1, 2. Right? I've really said two equations here. Okay, so I've applied the induction hypothesis. Now what do we do? Well, we just try to take these two pieces. You know, this is thinking through an induction proof is a lot like thinking your way through a recursive algorithm, right? In a way, we've split the problem into two subproblems. We know by the induction hypothesis that the problem is solved, as it were, right? Because the theorem is true for smaller subproblems. And so therefore we try to recombine what we have into a solution to the original. We somehow recombine the truth of the theorem for those two smaller pieces into the truth for the tree on m edges that we started with. Okay. Okay, one more thing I have to say. Since no vertices were removed, we have that the sum of the number of vertices in T1 plus the number of vertices in T2 must equal n, number of vertices in the original tree. All we did was erase an edge. We did not erase its two end vertices. And that split into two trees. So we chose an edge at random, split it into two pieces. Okay, therefore, what? Therefore, well, I'm trying to show that m equals n minus 1. M, that's the number of edges in T. Well, that's the number of edges in T1 plus number of edges in T2 plus 1. And what's the 1? That's the one I erased, the one we removed. But by the induction hypothesis, as we saw, this is number of vertices in T1 minus 1 plus number of vertices in T2 minus 1 plus 1. Cancel a couple of 1s, and I get number of vertices in T1 plus number of vertices in T2 minus 1. But, as we saw, these two add up to n. This is n minus 1. And that's what we wanted to show, m equals n minus 1, as required. Notice everything I did here is identical to the last time I proved this. What's different, the only thing that's different, is it's all phrased in terms of induction on the parameter m instead of induction on n. Okay, so why did I bother to do that if it's so similar? Because I want to generalize this in a couple of different directions. And in one of the directions of generalization, it only really works well if you're doing induction on m. If you're doing induction on n, it doesn't generalize well. Okay. So here's lemma 2. This one is not the one I'm talking about. It's the next one after this where you need m. Lemma 2 says if G is acyclic, remember what that means. No cycles, but not necessarily connected, with n vertices, m edges, and it might have more than one connected component, and k connected components. So, remember what a connected component is? It's a connected subgraph that can't get any bigger and stay connected. You can't have any bigger, any containing subgraph within that graph that is still connected. So they're the maximally connected subgraphs of a graph. So we have n vertices, m edges, and k connected components. Then m equals n minus k. Notice that this is a true generalization, because if G were a tree, then it would be acyclic and connected, which means it would have exactly one connected component. K would equal 1, which means this would say m equals n minus 1, which I just proved. Right? So we proved a special case of this already, and so this is a generalization to possibly disconnected but acyclic, still acyclic graphs. How do we prove this? How do you think we prove it? If you said induction, you're wrong. Huh? By cases, I wouldn't put it that way. It's basically just applying the previous result to each connected component. That's what you have to do. And then add up the results. Some people, when faced with this on an exam, try to do it by induction. Those people have gone induction happy. Sort of the opposite of what well, I guess some people would try to run and hide from induction, and other people, okay, all proofs are induction proofs now. Right? Some proofs aren't supposed to be induction proofs. This one isn't supposed to be an induction proof. Does it sound like I'm laughing at students behind their backs? I'm not. It's not behind your back. I'm right here. No. I'm just. It's all in good fun, of course. All right. So what do we do? Well, first of all, G is acyclic and it has k connected components. Each of its connected components is connected, and of course acyclic. Right? By throwing out edges and vertices, you can't create a cycle. So each of its connected components is both connected and acyclic, and therefore a tree. So let T1, T2 up through Tk denote the connected components of G, which are necessarily trees. Okay, so by the last result, other notation, let Ni, Mi denote number of vertices and number of edges in Ti. I going from 1 up to k, of course. Okay? So Ni is the number of vertices in the ith component. Mi is the number of edges in the ith component. By the previous example, or by lemma 1, the previous result, that's a 1, believe it or not. By lemma 1, we have that number of edges in Ti equals number of vertices in Ti minus 1, i.e. Mi equals Ni minus 1. This is for I going from 1 to k. Okay? So, what's M? M is, that's the number of edges in G, in the full graph. Well, that's got to be the sum of the number of edges in each of its components. This is the sum. I equals 1 to k of Mi. And by what I just said, by lemma 1, each Mi is Ni minus 1. Now, what should I do with that sum? Any ideas? It's got two terms in the sum. Say again? Split it, yeah, split it. So this is equal to the sum I equals 1 to k of Ni minus the sum I equals 1 to k of 1. All right, so if I add up all the vertices in all the connected components of G, I get the total number of vertices in G. What happens if I add up k ones? What do I get? K. So this is minus k. And that's exactly what we were supposed to get, n minus k. See how simple that is? So I consider the first problem to be moderately, or well, since we've gone over it twice, now only moderately difficult for the midterm. I consider this to be even easier, right? Because it's just take a result and apply it to a bunch of components and add up the result. Okay, now I'm going to generalize lemma 1 in another direction. Lemma 3. So, if G is connected, remember what that means. You can get from anywhere to anywhere. Every vertex is reachable from every other vertex. With n vertices and m edges. Number of components is necessarily 1. Then m is greater than or equal to n minus 1. So do you see how this is a generalization? Certainly if G were connected and acyclic, namely a tree, we already showed in lemma 1 that m is equal to n minus 1. So if m is equal to n minus 1, it's certainly greater than or equal to n minus 1. So we've generalized in another direction, right? In lemma 2, we dropped the requirement that the graph be connected, but still acyclic. In lemma 3, we dropped the requirement that the graph be acyclic, but it's still connected. So we get an inequality in this case. Okay, so how do we prove this? This proof is a proof by induction, and it's a direct generalization of the induction proof I showed you a few minutes ago. Prove. Okay, so 1, we'll start with m equals 0. If m, this is the same base case as before, if m equals 0, G being connected can have only one vertex. So n equals 1, and so therefore m equals, m equals 0, which is greater than or equal to 0, which is equal to n minus 1. Right, it's a triviality. Okay, step 2. This is where it's different. Let me repeat the script, or the form that you have to fill in, right? The script that you're following. For all m greater than 0, if p of 0 and all the way up to p of m minus 1 are all true, then p of m is true. This is the strong induction hypothesis. All dominoes starting at 0, ending at m minus 1 have fallen. Show as a consequence that the mth domino falls. So how do I start? Let m be greater than 0. Be chosen arbitrarily. Okay, I'm being a little bit verbose there. If you don't include that sentence, you'll lose at least a point, maybe 2, because it's like writing a Java program where you use a variable, but you didn't declare the variable anywhere before you used it. Okay, it wouldn't compile, right? So this proof won't compile if you don't have this sentence. I really, really wish I had a proof compiler. I wish I could just take everybody's proofs and feed them into an optical character recognition thing. And then from there, it would be digitized, and then it would be sent to the proof compiler, and the proof would return compiles or doesn't compile. And then not only that, it would run the proof to see if it's logically correct. Okay. Somebody invent that, please. Okay, so what do we assume? We've got to state the induction hypothesis now. Assume what? What's the best way to say that? Assume for any connected graph, G prime, different letter, that number of edges in G prime is greater than or equal to number of vertices in G prime minus 1. Okay, that's the explicit statement of the induction hypothesis. Okay. Well, we're going to do exactly what we did in lemma 1. We're going to pick an edge and remove it. Pick any edge in edge set of, oh wait, I've got to say, sorry. Let's throw that away. I've got to say everything right, because I insist you say everything right, so I better do it right in my examples. We must show that P of M is true if G is connected with M edges N vertices, then M is greater than or equal to N minus 1, right? So we also have to explicitly state the must show, at least to get full credit in this class. Okay, so pick any edge E in G and remove it. Okay, so G is connected, but it's not acyclic. So when you remove an edge, it could stay connected, right? If you removed an edge that belonged to a cycle, then those two ends are still reachable around the backside of the cycle, right? So just because, since there are no cycles, if there were no cycles and you removed an edge, then there would be no way to get from one vertex, one end to the other. That's why it splits into two. All right, so now we have to split this proof into two different cases. By the way, there's a name for those kinds of edges. An edge whose removal disconnects the graph is called a bridge. By erasing it, you disconnected it, or at least increase the number of connected components by deleting that one edge. Any edge that's not a bridge must belong to a cycle. Go ahead.
I have a question about something you said earlier.
Yes?
Does the symmetry imply isomorphism or the other way around?
No. What kind of symmetry of what? And
What's the relationship between symmetry of a graph?
what do you mean by symmetry of a graph? I know what symmetry of a relation means. What do you mean by symmetry of a graph?
About isomorphic, the only thing I can think of is symmetric, like it has these properties.
Okay. I'm not going to answer the question on the grounds that it's not quite well defined or not quite well formed yet, because I don't know what you mean by symmetry of a graph. Relations have the property of being symmetric, right? A relation on a set is symmetric if AX, X related to Y, if and only if Y related to X. I'm sorry, yeah. X related to Y implies Y related to X. Not necessarily. I don't know what symmetry of a graph means. That's why I can't answer it. Okay, so so pick any edge and remove it. We have now two cases. Case 1. Case 1 will be the easy case. The result, which I'll refer to as G minus E, is still connected. but it has one less edge than G did. So we can apply the induction hypothesis to it. Note, G minus E has n vertices and m minus 1 edges. By the induction hypothesis, applied to this graph, which has fewer edges than the original, this gives m greater than or equal to it gives number of edges, which is m minus 1, greater than or equal to number of vertices minus 1. Right? Number of edges greater than or equal to 1 less than the number of vertices. So therefore, m is greater than or equal to n, but n is certainly greater than n minus 1. So therefore, trivially now, m is greater than or equal to n minus 1. As a matter of fact, I could write strict inequality. This is the case where strict inequality actually holds. So I got the result I want in the special case when G minus E is connected. And as far as induction goes, this could have been weak induction, couldn't it? Because I'm relying on the domino immediately preceding the mth domino, the one indexed m minus 1. Now we have case 2. Case 2. In that case, G minus E is disconnected. Now, as a separate claim, which I will not prove here and is proved in the handout, and I would not ask you to prove this claim on an exam, G minus E in this case consists of two connected components. Call them G1 and G2. Proof is in the handout. Okay, so that is a side note. I'm just going to use that fact. Okay, so I have two connected components. Note, since these two components are subgraphs of the original graph, or actually each of them are subgraphs of this graph, which has fewer than m edges, each of these has fewer than m edges. Note, the number of edges in GI is less than m for I equals 1, 2. I mean, this is the part of the proof that copies pretty much exactly what we had in lemma 1. So, by the induction hypothesis, we have number of edges in GI greater than or equal to number of vertices in GI minus 1. This is for I equals 1, 2. Okay. So what did we do in lemma 1 at this point? We just then said, oh yeah, also number of vertices in G1 plus number of vertices in G2 equals n, since no vertices were removed. You see how this parallels exactly lemma 1? Thus, M is equal to number of edges in G1 plus number of edges in G2 plus 1. What's the 1? The one we removed. But this quantity is greater than or equal to number of vertices in G1 minus 1 plus number of vertices in G2 minus 1 plus 1. This is by induction hypothesis. Actually, I already said that up here. I don't care where you say it. You could say it more than once. You're not going to lose points. But you got to say it at least once, where you're using the induction hypothesis. So this is equal to, cancel a couple of 1s, number of vertices in G1 plus number of vertices in G2 minus 1, which is n minus 1. So if I just string these all together, I get m greater than or equal to n minus 1. Therefore, m greater than or equal to n minus 1. That's the end of case 2. In each case, this pen is out of gas. Hang on a second. In each case, m is greater than or equal to n minus 1. End of proof. Okay, so that was lemma 3. A little bit more complex because it splits into cases, but one of the cases was trivial. The other case was just like lemma 1. I have placed this problem on midterm 2 in the past, and I have placed it on final exams in the past. Okay, it's a little bit longer, but it is a more involved induction proof, a little bit more the kind of induction proof that I'd expect people to be able to get through by the time they're out of this class. Okay, so guess what comes next? We just finished lemma 3. Let's do lemma 4. Lemma 4. All right, so lemma 4 is a generalization of lemma 3 in the same way that lemma 2 was a generalization of lemma 1. That is to say, I'm going to relax the connectedness. So now G is going to have multiple components. So if G is a graph, nobody's assuming it's connected, nobody's assuming it's acyclic, with n vertices, m edges, and k connected components, then m is greater than or equal to n minus k. Remember, in lemma 2, we had equality here. All right, so the proof of this is very similar, in fact, almost identical to the proof of lemma 2 from lemma 1. Proof. Let G1, G2, GK be the connected components of G. Has K of them. Let's give them names. So these are all connected. So I can apply the last lemma. By lemma 3, we have number of edges in GI. I tell you what, let's introduce some notation. Let MI, NI be the number of edges and number of vertices in GI, I going from 1 to k. By lemma 3, we have mi greater than or equal to ni minus 1, since the GI are all connected. They're connected components. And that's all lemma 3 required, connectedness of the graph. Thus, m, which is the sum of the number of edges in each of its components, I equals 1 to k, is greater than or equal to, see, before we had an equal, but now we only get inequality. I'm basically adding up all these inequalities. Sum I equals 1 to k, ni minus 1. But just like before, I can split this into 2. This is sum I equals 1 to k of ni minus the sum I equals 1 to k of a bunch of 1s. But this is equal to n, right? Number of vertices in each component added up gives me the total number of vertices in the graph. Add up k1s, I get k. So with this inequality here, I get m greater than or equal to n minus k, which is what we wanted. Okay, there's 4 lemmas. I have a couple of more lemmas I'm going to do on Friday. State a big theorem that I call the treeness theorem that's in the it's in the appendix. Partially prove it. Some of it's already proved. Then we'll talk about graph representations, a little bit about directed graphs and a little bit about graph representations. If you did not pick up your homework from last week, it's out here and it's in partial, close to alphabetical order. If you did not turn in your homework that is due today, please place it up here now and do it all very neatly. I don't see a traffic jam. That's good. That's a miracle. Hi.
Question.
Yeah.
Proof of lemma 3.
Yes?
So like